Hey everyone, we're Group 72, and our problem is on energy and momentum. Starring Ashley Basilio,
Amy Ty,
Chris Lee,
and Bryant.
a man at a shooting range fires a 9mm handgun at a target suspended from the ceiling. The bullet from the handgun becomes embedded in the target's center of mass. 90% of the bullet's kinetic energy is lost as heat upon colliding with the target. The remaining 10% is transformed into kinetic energy for the combined mass of the embedded bullet and the target after the collision. How high does the target's center of mass swing after the collision relative to the position of the target's center of mass prior to the collision? Given in the problem, we have M1, the mass of the bullet, is 0.010 kilograms, M2, the mass of the target, is 1 kilogram, V1, the velocity of the bullet, is 20 meters per second. For this problem, assume that the bullet travels at a constant velocity, neglect air resistance, and assume that the ropes used to suspend the target are massless and frictionless. Pause the video now to try and work out this problem on your own.
So here we have two diagrams. In the first diagram, we have two objects, the bullet and the target. In this diagram, it shows the bullet after being shot from the handgun, but before making impact with the target. In the second diagram, the bullet has now made impact with the target embedding itself at the center of mass at the target. This collision swings the target containing the bullet in a backwards and upwards direction. Our goal is to solve for the height difference.
For the first step, we're calculating the bullet's kinetic energy prior to the collision. Here we have the kinetic energy equation, Ke equals 1/2 mv squared. Then we plug in the mass of the bullet, which is 0.010 kilograms, and the velocity of the bullet, which is 20 meters per second. Finally, we solve to find that the kinetic energy of the bullet prior to the collision is 2 joules. For the second step, we're calculating the remaining energy after the heat loss of the impact. Now remember from the problem that 90% of the bullet's kinetic energy is lost as heat. We calculated in the previous step that the kinetic energy of the bullet prior to the collision is 2 joules. So we multiply 2 joules times 0.9 to find the kinetic energy that's lost as heat. Finally, we subtract the amount of kinetic energy lost as heat from the total amount of kinetic energy of the bullet prior to the collision to find that the remaining kinetic energy of the combined mass of the bullet and the target is 0.2 joules. The third step, we're solving for delta y. Now we have to think about how the kinetic energy immediately after the collision is equal to the gravitational potential energy of the combined mass at its highest point. This is true because the kinetic energy immediately after the collision pushes the combined mass of the bullet and the target up to some delta y. In the process, the kinetic energy is transformed into gravitational potential energy. Now we calculated in step 2 that the kinetic energy immediately after the collision is equal to 0.2 joules. Below we have the equation for potential energy, Pe equals mg delta y. We equal these two to each other and plug in the kinetic energy as well as the combined mass and the acceleration of gravity and solve for delta y, which turns out to be 0.02 meters.
alternate incorrect methods of solving. It is easy to make mistakes involving significant figures. Trying to solve for delta y using velocity vectors and kinematic equations is nearly impossible. Disregarding heat loss results in an incorrect answer. Physics principles: the law of conservation of energy, kinetic energy, gravitational potential energy, and energy transformations.